Pedro is Technical Director at FCT Combustion America, located in the US and Brazil. He's a chemical engineer holding a BSc, MSc, and MBA, having obtained his master's degree in NOx emission reduction in clinker kilns. Pedro holds patents and has developed novel processing routes for fertilizers with the University of Cambridge. An experienced pyroprocessing technician, Pedro has served the cement, industrial minerals, lime, and fertilizer industries over the last 25 years in both technical and managerial positions. So someone with a lot of expertise, a great technical background, and he's going to talk to us today about FCT calcined clay technologies. Thank you, Pedro.
Thanks, Toma. Well, welcome to our session here. Thanks for the time. Well, just a quick introduction on the company, what is FCT, but the agenda is talking about FCT, the CO2 reduction we bring cement and options that we are exploiting, and some case studies that we have gone through. So first about FCT. FCT has been established a long time ago in '85. We have a large experience in cement, lime, and minerals. We have a worldwide presence and more than 1,000 references in this market, being more than 300 only in cement. So we've been around for quite a while on cement. FCT has 3 branches, one for combustion, which we're talking about industrial combustion, and then we have flames for decorative events and Olympics, where we have special flames, and also online analyzers, which is a different brand from the same company. But let's focus on combustion now, which is the part of the company I work for. And basically what we are capable of delivering as a company, we're not only burners, but also valve trains, BMSs, and everything around the cement plant, including the calcined clay technology, both for rotary and flash calcination, and all the subjects related to it. Quickly going to the CO2 reduction, we know we've been struggling to get some positive reduction on the man-made CO2 emissions, and there's a quite share of contribution coming from the cement industry. So we are excited to be part of this contribution to the world reduction on CO2 emissions via the calcined clay technology. As we know, simply we are not talking about too much on calcium anymore. We are more focusing on aluminum silicates, where we want to remove the water content on it and transform it into amorphous but still very reactive with fairly low compared to cement the temperatures, where we can pull out what we need to activate those pozzolans. And the key here is to understand how does the reaction go. So what we have here is a thermogravimetry, where we see the steps of the reaction. First, we remove the moisture, and then we activate the clay, and we try not to crystallize the clay. So we try to progress with the reaction to this point here, and we try to get to some 800 degrees for getting there. But we want to avoid this undesired conversion that from amorphous to crystalline structure, and this is very important to what comes next in the presentation. So, while some of the options important being that the activation of clay can happen both in a flash calciner or in a rotary kiln. The most conventional form of doing this is the rotary kiln. The most efficient way would be the flash calcination, and both are very, very attractive. Each of them has its own advantage. We're going to go through them right now. So when we're talking about the rotary kiln, we call it the rotocalcs. We can deal in existing equipment. We can convert existing equipment, or go with a whole new supply of a plant. The interesting thing about this technology is that we can combine drying and calcination in single equipment. Of course, we're talking about drying from, say, 35% moisture down to what's necessary for calcination. But if you don't need an auxiliary drying up front, and we apply a burner for a main source of heat, and also we can use a combustion chamber to fire the process depending on the specifics of the project. On the flash calcination, the other way, it's quite comparable to a conventional pre-calcining kiln, preheated tower, where we have preheat stages, we have a combustion chamber, we have a calcining path, and then you have a cooling process. It has different possibilities, but we know we can enhance the heat recovery, and we can have a tailor-made solution for each case. So talking about the feed and preheating, we use the exhaust gas for drying. We use a bucket elevator to feed the system, so it's very, very energy efficient, but also we can recirculate it. So in case of any shutdown of the plant, we can quickly restart. But meanwhile, we can recirculate the material, so won't be so much of a loss of material, not reactive one. On the calcination itself, there are different ways of doing it. It can be an inline calcination, or it can be a separate line calciner. It depends on the source of heat and how you set up the plant. And we do have optional color management features. So for flash calcination, it's also possible to manage the color if needed. And cooling, we have different setups as well. We have a suspension cooler. We can have a rotary cooler, again, depending on the feedstock and what are the targets for the process. So the good thing about the flash calcination is that it has virtually almost no refractory, only on the combustion chamber, rising and calciner itself. So it implies a very quick heat up, while we're talking about a regular rotary kiln where you take about 24 hours to heat up. In this case, you can go for 2 hours to heat up the system up to speed. The other thing is it's well known for the cement producers. There's no moving parts, so you can have a low maintenance or a very light structure and very reliable one. The other feature of the flash calciner is that you can achieve a very precise control. So we can prevent melting, you can prevent agglomeration of the clay. You can lead to a very reactive and high surface pozzolan, which is very welcome. Again, remember when we've been talking about the temperature control and how we want to avoid crystallization of the structure. So when you need and you have to have a very precise control, you can achieve that with the flash calciner. Of the standard units that we have, we talked in tons per day. We're talking about over 1,000 tons per day of flash calcination. It's already achievable. And there's an actual installation where you can easily put together, depending on the size. You can also truck it and using mobile equipment and reducing the erection cost. But what we have finally with the flash calciner is a very reactive pozzolan. You probably don't need to grind the calcine, as the material is not prone to melt or to re-agglomerate. As we've seen the quick start and easy operation of the plant. So basically, it's a quick setup. You have a lower fuel consumption compared to rotary kiln, so there's less of radiation and less of losses for convection. You have a lower maintenance cost, and overall, it's a very lower electrical consumption. And in the end, you have a faster ROI depending on the existing equipment you have on the plant. Before calcine and flash calcine, you have to dry the material. So you can have different options. We can supply rapid dryers. We can supply a vertical roller mill with the feature of sand extraction. And it's incredible the amount of sand you can have with this inert material. And you can remove the sand from the material to be sent to the calciner, which is advantage from a reaction point of view on the product performance. And we can also apply the rotary dryer as a solution for pre-drying the material. As for the hot gas generation of the source of heat, You can use that's a simple gaseous or liquid fuel, hot gas generator, pulverized solid fuel, or even the fluidized bed for coarse and alternative fuel. So it all depends on the availability of fuels and the needs and the flexibility you wanna have. I'm especially excited of using this technology of the fluidized bed because again, no moving part of there. It's static equipment. You don't have to even grind the solid fuel up front. So you can really rely on a very, very, very good control and a good thermal inertia and a very, very precise temperature control. So these were the pieces of equipment available. It depends from case to case. So now we're going to show quickly case studies from different conversion or new plants we've been studying with our clients. So basically, we take an existing preheated kiln. So many people have kilns, they have idle kilns. They wanted to convert to calcined clay. So let's pick an example here of a 4-stage preheated kiln. It's kind of a very common size of a kiln of 4.1 per 60 meter long, planetary cooler kiln, producing a 1,000 ton per day clinker. It's a coal-fired system. It's a clay with 11% LOI, 20% moisture, kaolinite kind of clay with low iron, and it comes coarse. So question would be for this case that what's the capacity of this kiln when we convert it to calcined clay, a 1,000 ton a day clinker kiln, and can we use this kiln to produce both clinker and clay, and what to do to make it work, and what are the benefits or what the disadvantage of having a swing kiln. So let's split this first case in two scenarios. One where we want a swing kiln, so it will produce clinker and clay, and will be running in both scenarios. And the other one just fully converted to a pozzolan kiln. So if we go for only pozzolan, the rationale here is that we can install lifters, and by installing lifters, we increase the drying capacity, and we probably debottleneck the kiln for high moisture feed. So whenever the feed is high, you have to have a very huge drying section on the kiln, so it may bottleneck the kiln capacity. So the other thing is that the coarse material is very welcome for an existing rotary kiln. So we're going to have low dust recirculation. So when the feedstock is not prone for dust generation, you can use higher velocity and profit from higher kiln capacity in the end of the line. So the modification for the pozzolan only is to install the lifters in the drying zone. We have a sizer, we have a grizzly, you have to separate the big chunks in order to convey it to the kiln inlet and feed to the system. Of course, you have to add a raw clay transport system, and our combustion chamber has to be evaluated, or combustion system overall has to be evaluated and adapted for such low temperature burning zone. So in the end, the 1,000 tons a day kiln became a 1,050 tons per day pozzolan kiln. We have this heat consumption of 570, most of it related to the drying. And then you have a 32 out of 60 meter long of the kiln for drying and 28 for calcination. This was possible to reach the same level of production in clinker because you're using lifters. But then we go to the other scenario where we want to swing the kiln to between clinker and pozzolan. So the rationale, we cannot touch and change, put lifters on that. So we're going to decrease or have a lower drying capacity. In this case, we do probably almost everything but the lifters for keeping it as a swing kiln. And this will lead to a 750 tons a day, 610 kilocal per kilo heat consumption. We're going to have a longer drying zone, and we have a 20% moisture removal capacity. But if this feedstock varies from 20% moisture up to 30% moisture, things can change drastically, and the kiln can lose production from 1,000 to 750 on pozzolan, and then 480. And a higher heat consumption, of course, you're drying more water. You have a longer drying section, and then you have to dry all the 30% moisture. So this one shows us how important is the drying section and the kilns. And if you want to boost the kiln capacity, you must probably install lifters in the drying zone to cope with probably the same level of production as you had in clinker. So in this case, you're going to have lower capacity, but it's still possible to swing the kiln back to clinker. And sometimes it's just have 3, 4, 6 months of kiln idle capacity, and then you can lower the investment and start producing right away with very few modifications. So it's not only disadvantages, but you can, although you're going to be producing less, but it's still going to be producing this and back to clinker if necessary be. So this was a case for a conversion of an existing kiln. Now we're going to go to a greenfield with a very constrained footprint in the plant. So you might want to use a tower instead. You go for the same 1,000 tons a day calcined clay for a matter of comparison. You want to use a lump petcoke. You don't want to dry the petcoke. You want to use biomass as well. And you start with a clay that's 7% LOI with 15% moisture, high iron, and more light. And what does it mean when you're talking about more light and low LOI? It means that you have this window of temperature between what is activation of clay and what is crystallization of clay, very narrow. So you have to have a very precise control of temperature. So the solution goes through a flash calciner. So what does it mean? If you have a footprint constraint and a strict temperature control, you need a short dryer, you need a flash calciner. You want to use biomass, or you want lumpy petcoke, so you're going to go for fluidized bed, hot gas generator. If you want to have color control, you can use water quench with suspension cooler, or even inorganic modifier, which is a special feature from FCT. We can talk about this later. Let's draft to the cooler ID fan, which means that we're going to have a savings on electrical energy. So it's a greenfield, a very efficient one, where we want a strict controlling temperature and all that. So the solution goes into a flash calciner with a hot gas generator, a fluidized bed version of it, in a short and 3-step dryer up front. So, and you're going to use a heat both for the drying and for the flash calciner, and you also recuperate some heat from the preheated tower into the drying section. So the solution is this: a rotary dryer, 2-stage preheater, 1-stage calciner, 2-stage suspension cooler, a fluidized bed, and a quenching with cooler heat recovery. So we want to control color here in this case. And the main KPI here is you're going to have 570 kilocal per kilo, 460 only for calcination. Some of the heat is wasted for quenching down and keeping the color control running. And you're going to have this 12 kilowatt hour per tower draft. So these are the key factor for this case. And if we compare those cases that we've presented before in a sort of qualitative way, we can say that case one with existing preheated kiln, you're going to have a lower capex compared to these no lifter changes. And it's going to be the lower capex, but of course a lower capacity as well. On OPEX, you're going to have low, medium, and the lowest one being the flash calciner. It's a different scenarios, and you have 20% moisture, and then you have 15% moisture. And the heat consumption as well, it all depends on whether or not you're going to apply the lifters for the case of the rotary kiln, and if you're going to apply or not quenching for color control. So we can be very efficient as low as 510. Sorry for that. But it can go as low as 510 without quenching for 15% moisture. So the message here is that there is not such thing as a best option. We just have to see what we have available as machinery. What are the main target? Is it going to be efficient? Is it going to be a quick turnover? Is it going to be just getting started, or how efficient we want to get? So in all studies, we offer two phases of studies where we go and exploit the mining model and the cost. We can characterize the clay. We go into all the different aspects of it, and we check on the existing equipment. After doing this first phase of analysis, FCT goes into a second phase where we're going to go more deep into the raw material handling and preparation. We're going to study more on the residence time, the discharge temperature, drying, calcination, recycles, color management. That's an important topic here. So we have to address the quenching, the reducing atmosphere, the inorganic modifiers, all sorts of things that you have to address to get the right color to your product. And we can refine the CapEx towards a firm quote for the client. So why should you choose FCT? We've been already involved in over 13 Puzzle rotary kiln projects in the world. We've been doing this since the 80s. There was a project in Brazil back in 81 for the first conversion of our existing rotary kiln. We do not address only equipment supply, but also quality and process tests. We know that we have to do a lot of studies in rheology and durability and all that. So we need to have a very, very comprehensive analysis of the subject. We are experienced cement, fuel, and combustion specialists. We have an in-house CFD also, so we can optimize before even erecting the plant. And we can also conduct an in-depth clinker quality and reactivity assessment to boost quality results in LC3. So most of the time, people are focused on getting the right pozzolan, but also you can try to profit from a better clinker, and we can help you with that. So there are several solutions for calcined cleaning, and with this, I'm wrapping up my presentation. Trade-off studies have to be conducted. There's not a single solution. We don't prefer one technology over the other one. We're ready to support the clients in selecting the most appropriate technology and deliver the best solution to produce high quality activated clay. And the final message is that the transition to LC3 requires knowledge not only mining, logistics, clinker, and also concrete technology, thermal fluid dynamics, grinding, and so on. So we're up to do this, and we can provide all this at once. So with that, I finish my presentation, and thank you for your time, and hope to have helped somehow.